Imagine if we could see the world around us, not just in 2 dimensions, but in 3. We'd be able to map buildings, forests, and even weather patterns with incredible detail. Thanks to a technology called LiDAR, we actually can. Light detection and ranging, otherwise known as LiDAR, gives machines the ability to see the world in 3 dimensions. And it's been quietly powering many of our favorite technologies for decades. The story of LiDAR begins in the early 1960s, when the Hughes Aircraft Company set out to create a new type of ranging system that could measure distances more accurately than radar. At the time, radar had been around for decades and was commonly used in military applications to detect aircraft and missiles. But radar uses radio waves to measure distance, and it wasn't precise enough for many applications. That's where light came in. By using lasers, which were just beginning to be developed, Hughes engineers were able to create a ranging system that was much more accurate. They called it COLLIDAR, short for Coherent Light Detection and Ranging, and it would later become known as LiDAR. In the simplest terms, LiDAR works by sending out laser beams and measuring how long it takes for them to come back. By knowing the speed of light and the time it takes for the light to return, we can easily calculate the distance to the object. In fact, all LiDAR systems work on this principle, but how exactly they do it can vary greatly depending on the application. Some LiDAR systems use a single laser to scan the surrounding environment, while others use multiple lasers to do it more quickly and accurately. Some systems use rotating mirrors to scan the area, while others use a technique called frequency-modulated continuous wave LiDAR, which uses changes in the frequency of a laser beam to measure distances. Regardless of the specific method used, all LiDAR systems follow the basic principle of sending out laser pulses and measuring the time it takes for them to return. But why is this better than other ranging methods? LiDAR uses light waves, while radar uses radio waves. Shorter wavelength of LiDAR allows it to detect much smaller objects and create a more detailed, high-resolution point cloud. Additionally, lasers are much more precise than radio waves, meaning that LiDAR systems can measure distances with greater accuracy. This makes LiDAR ideal for applications that require high levels of precision, such as autonomous vehicles or surveying. Furthermore, LiDAR systems are relatively small and lightweight compared to traditional radar systems, making them easier to integrate into smaller devices such as drones or robots. One of the most well-known applications of LiDAR is in the field of autonomous vehicles. Self-driving cars must be able to perceive their environment in 3D to navigate safely and efficiently. And LiDAR is a key technology that enables them to do so. LiDAR systems mounted on top of autonomous vehicles can create detailed 3D maps of the surrounding environment, which allows the vehicle to detect objects such as pedestrians and other cars, as well as features such as traffic lights and road signs. This information is then used by onboard computers to plan a safe route and control the vehicle's movement. Not only does LiDAR help autonomous vehicles to see their surroundings in greater detail, but it also provides them with accurate information about the distance to objects, which is essential for making split-second decisions in emergency situations. As the technology continues to improve, LiDAR is expected to play an increasingly important role in the development of autonomous vehicles, helping them to become safer and more efficient than ever before. Another industry that has benefited greatly from the use of LiDAR is surveying and mapping, both terrestrial and aerial. One example is in the field of topographic mapping, where LiDAR can be used to create highly accurate and detailed maps of terrain. By using LiDAR to measure the distance to the ground at various points, surveyors can create a 3D model of the terrain, which can then be used for a variety of purposes, such as in urban planning or environmental management. Another application of LiDAR in surveying and mapping is in the field of construction. It can be used to monitor the progress of construction projects and ensure that they are following the plans. For example, LiDAR can be used to measure the height and width of buildings as they are being constructed, ensuring that they are built to the correct specifications. Additionally, it can be used to create 3D models of buildings and other structures, which can be used for a variety of purposes, such as in architecture or engineering. Overall, the use of LiDAR in surveying and mapping has revolutionized the way that these industries operate, providing a fast, accurate, and efficient way to capture and analyze data about the physical world. LiDAR is also being used in the exciting field of archaeology to help researchers better understand ancient civilizations. By using LiDAR mounted on aircraft or drones, archaeologists can create detailed 3D models of archaeological sites without having to physically dig at the site. This allows them to explore potential sites from a bird's eye view, identifying areas of interest that may contain valuable artifacts or structures. For example, LiDAR has been used to map the ruins of Angkor Thom, an ancient city in Cambodia, and to identify previously unknown structures and artifacts. Additionally, LiDAR can penetrate the canopy of dense forests, allowing archaeologists to study sites that were previously inaccessible. This has led to the discovery of several important archaeological sites in areas such as the Amazon rainforest. By using LiDAR, archaeologists are able to explore and understand ancient civilizations in a more efficient and non-invasive way, leading to new discoveries and a deeper understanding of our history. LiDAR has also found applications in the forestry and agriculture industries. In forestry, LiDAR can be used to monitor forest health and biomass. By measuring the distance to individual trees in a forest, LiDAR can create a 3D model of the forest canopy, which can then be used to assess the health and density of the forest. This information can be used by forest managers to develop sustainable forestry practices and ensure the long-term health of the forest. Similarly, in agriculture, LiDAR can create detailed maps of crops, which can be used to optimize irrigation and fertilizer use. By measuring the distance to individual plants, farmers can identify areas of their fields that need more water or fertilizer, allowing them to use resources more efficiently and improve crop yields. Finally, let's talk about meteorology. LiDAR is used in meteorology to measure atmospheric conditions, such as wind speed, cloud formation, and the presence of pollutants and aerosols. By measuring the distance to particles in the atmosphere, LiDAR can provide valuable information about the composition and behavior of the atmosphere. For example, LiDAR is used to measure wind speed by measuring the distance to particles of dust or smoke in the air. This information is used to create weather forecasts and to monitor air quality. Additionally, LiDAR can be used to track the movement of clouds and other atmospheric phenomena, which can help meteorologists better understand weather patterns and make more accurate forecasts. Overall, the use of LiDAR in meteorology has led to significant advances in our understanding of the atmosphere and has helped meteorologists make more accurate and detailed forecasts. As you can see, LiDAR is a versatile technology with applications in a wide range of industries. From autonomous vehicles to archaeology, the ability to measure distances precisely and create detailed 3D models of the world around us has led to significant advancements in many fields. As the technology continues to improve and become more affordable, we can expect to see even more applications of LiDAR in the future. Thanks for watching. We hope you enjoyed learning about LiDAR. Until next time.